Okay, so the recording has started. I'm going to share my screen right now. Okay, so hope you guys can see the screen on the I've just been reminded that you need to do the module feedback. I only have about 14 people that replied, so apparently I need about 30. So if you have not, please help me to do this feedback. Okay, so back to the lesson. Last week, what we did was we talked a bit on query processing, and it deals with the how fast you carry out the query. So just as a very short recap, so we will use this model to ascertain how quick or how fast your queries are being done. So this will be based on the number of block transfers, the time it takes to transfer a block of data, the number of disks that you take, and also the time it takes to access a block. So the time, if you want to transfer B blocks and access S blocks, it will be B times T base T plus S times T base S. Okay, so this will be the so-called the framework that we work on. We talked a bit about this clustering index. So about what is the difference between the primary index and the secondary index. And primary index is when it is a sequential impression. So let's look at the previous one. So in this case, ID is the primary index. When department name will be it is a non-clustered, it will be a secondary index. If you go on to this so-called this new table over here, you will find that if we were to build an ID based on this column, this is in ordered form, and this will be considered the primary index. If you were to build the index on this ID, although this is the primary key, it is not ordered, so this will be the secondary index. Okay, so this is just a small how to say recap of what we covered last week. So I'm going to go ahead to the material for today. So we talked about a bit about how long it takes for us to access a single record on your file system. And on this, I will be doing a video on the lecture last week as well, at your request. So I'll probably put it up over the weekend or something like that. So we stopped over here at conjunctive selection operation. So conjunctive, so this is this means that we have a few conditions, theta 1, theta 2, all the way to theta n. So these are the different conditions. So all of the conditions must be fulfilled. Oh, sorry. And what happens is that if I'm only using a single index, so what it means is that out of the many conditions, there's only one index here that one of the attributes here that only has the index. So only one of them has the index, for example. And this is an instance of how the query may look like, where I have something whereby attribute is equal to something, and then another attribute is less than, greater, or smaller than another so-called a number. And if let's say we have the index to be built only on department name, what we do is we will use the earlier way of calculating the cost to find the index, how long it takes for us to get down to the computer science records over here. And after that, after we have the record in memory, then we will check on the other conditions. Okay, so let's look at this example. So this example is if let's say we have index on the department. So is this a primary or secondary index? So what do you think? Is this primary or secondary? So let me see. So the answer is primary, okay? Because this is sorted. And if you're building this, this will be a primary index because it is sorted, regardless whether it is it is a key or not, it's a candidate key or not. So once we have this, we can if you want, you can refer back to the cost for this is a primary index on a non-candidate attribute. So it will be, and it's an equality, primary index equality on a non-candidate key. So this will be the case that will happen. So just as a recap again, this is a B plus tree. So what we want to do is we want to find where are all the instances where the tuple may reside. So the equality in this case is on the department, and we know that it is a primary key. Primary index. It is a non-candidate key. So there are many instances of department equals to computer science here. So we talked about this last week. The height of this tree is going to be rather the cost of accessing down the height of the tree is going to be the height of the tree multiplied by the time of access plus the time of reading. So this is how long it takes for us to get down to the leaf of the tree. The other cost here is how long it takes for us to access the individual elements of the, or rather the individual blocks of the leaf in order to find where our tuple resides in. And as you know, this is a non-candidate key, so it will occur in more than one of the blocks. So there is an initial access of finding this non-candidate key, and after that we need to go through all the different blocks in order to seek out where my tuple resides in. Okay, so the cost of this will be similar to the cost which we saw earlier, but the only slight difference is after you have gotten down to the leaf of the tree, and you find these are the tuples with computer science, you will then check all the other conditions to see if they fulfill the conditions of the join, and you do it in memory. So there's no disk access that's being done when you're doing all the other checks. Okay. Is this clear for all? I hope this is fine. Okay. Let's go on to the next slide. So this is exactly the same. The only difference is that I'm now using a composite index rather than a single index. So in the composite index, it means that they are treated as one main index. So I have department name and I have salary. So in this case, right, do you think this index, would it be a primary or would it be a secondary index? Yeah. So intuitively, there's no order, and so this would then be a secondary index. Okay. And if we go back to how it looks like on the secondary index, so this will be a secondary index 3, and it is somewhat the comparison. So this will be the cost structure. So the height of this is similar. It usually is the same. The difference is only sorry, this is a primary. Sorry, not this one. This one, yeah. The height of this is the same. Usually it's the same. The difference is only in this part, whereby right now you have to do a access and a read for every single block, because it is a secondary index with comparison. It is not sorted in order, so you need to do an additional this access for every single block. Okay. Very quiet again, but I assume that everybody is understanding and nodding their heads. Okay, let's go to the next one. So conjunctive selection using multiple indices. So for this, you have to retrieve records from different indices and perform intersection of the sets of record pointers. So for example, if you have computer science, or rather department name, and you also have salary, and in this case, you have two index over here. So it may well be that one is a primary index, one is a secondary index. In this case, both of them are secondary indexes. So in this case, both of these records are secondary indexes, and yeah, and so this will be similar to what we have in the composite index, where you are actually assessing them as a secondary index. So the only difference is again, rather it is very similar in the sense whereby after you have gotten the different records, one from computer science and the other one from salary, greater than 70,000, you then check them in memory. So is there a question? Okay, all good with this? Okay, if all is fine, I will go on to the next slide. So earlier it was conjunctive, so it was all the ends. So it must be this and this and this and this. Now we are moving to the disjunctive selection, which are the ors. So in this case, if you talk about using indices, It is possible, but it's normally probably highly unlikely that unlikely all attributes are indexed. At least in practice, it is highly unlikely that this occurs. And so what you usually do is but not what we what is usually done is that a linear scan of the entire relationship has got to be performed. So when we do disjunctive selection, so it is common to unfortunately carry out a linear scan of the relationship. Okay. Can. Yeah. So in this simple case, so we are able to use indices because all the attributes are indexed. So this will be similar to this case. Okay, can you see the similarity? So the cost of this will be similar to this. So similarly, we have both of these cases have multiple indexes, same as this, multiple indexes. And so the cost of this two will be the same if regardless of conjunctive or disjunctive, if all the indices or rather all the attributes are indices. However, if there's only one, or rather if any one of these is not an index, then we have to carry out a linear scan. Okay, so far? Okay. So if everybody is fine with this, I'm going to move on to the next part. I believe everybody is listening very intently. So, yes, is there a question? Okay, seems that it's random noise. Okay, so let's go on to the next part, which is sorting. So take a minute to think, or a few seconds to think, why are we studying sorting in databases? Why is this being used in databases? Okay, so many of the queries, firstly, as you can see on the screen, sometimes you want the output to be sorted. Yeah, sometimes you may want it to be sorted, but there's actually one very good reason why, because items such as joins, they can be implemented very efficiently if we first sort them first. So I think we have done you have done this before in your 280 or maybe your 360. So you will realize that of course if you sort them first, then you're able to carry out these joins more efficiently. Of course, the downside of this is that insertion will be more expensive. Okay, but today we're not talking about this. So if we are fortunate and everything can be managed in memory, then we can just carry out quick sort or merge sort. If it doesn't fit the memory, then we will have to carry out the something that we call external merge sort, which we'll talk about it now. But before we talk about the merge sort, I understand that some of your colleagues here, they may not have the background of this. So I'm going to do a very quick illustration of what merge sort is. So merge sort belongs to a class of algorithms known as the divide and conquer. So, if you are doing a sorting, so let's say if I have a few numbers here, let's say I can't think of some random numbers. Let's say 30, 20, 50, 70, 10, and 2, 3, 4, 5. Let's do one more. 40. So there are two parts to this. The first part is when you do a divide step. So in the divide step, you will actually divide the array as much as possible into two parts. (70, 10, 40). And you then divide it again in two parts. 30, 20, 50. And you iteratively carry this out until you end up with single elements. If you want, you can also do this for consistency. So this is the divide part. So notice that at this divide part, no work is actually being done by the algorithm. So you are just playing around with the indices and no work is being done. All the work is being done in the merging part. So the merging is over here. So I'm going to copy down the numbers because I run out of space there. So so initially, if I were to, it's organized. So if I were to do the merging, I'll first start with these two elements first. So these two elements will be merged and they'll be sorted in the right order, which will give me 20 and 30. And this is going to give me 50 first. These two will be merged together to give me 10, 70. And this will give me 40. So this is the first step, first iteration of the, or rather first run of the merging step. In the next run, we're going to merge these two together. You can consider that to be, you have 2 pointers at the side. So you can think of it as you're having 2 pointers, one over here, one over here. You're going to compare between these two dot pointers. You take the first number first. So first will be 20. You're going to move the pointer over here, compare between these two numbers and take 30 and move this pointer to now, and now you only have 50 left. So same thing, you're going to start with 2 pointers here. So first you compare the pointers 10 and 40. 10, then next will be you move the pointer here, 40 and 70, 40. 40 goes to now, sorry, this pointer goes to now, and then 70. So final step, mouse is on. Final step, I have a pointer here and a pointer here. 10 will be compared to 20, 10. And 20 to 40, 20. 30 to 40, 30. 50 to 40, 40. 50 to 70, 50. And now 70. So realize that all the work of comparison is done at the merge step. Okay. So this has the or what they call the concur step. So what we consider this to be how to say something that we also say advantage of merge sort, other than it being fast, is that it is in memory. It is a sort that's in memory. So remember, I keep on talking about no work being done at the divide stage. So very little work is being done here. Usually we take the the cost over here to be close to 0, or rather you can call it even a constant. Over here at this step, you realize that at every single you can call it level iteration, we actually have to check through every single element here. So every single step, this takes a cost of n, because we actually go through every single element here. The height of this, and as we know, as we have studied in the B plus tree, if a tree has 2 branches, it will be log m base 2. So this 2 depends on the number of branches we have. If I have a B plus tree of 10 branches, so this will be log n base 10. So for merge sorts, you can consider the branching factor, fan-out factor to be just 2, and so the height of this tree will be log n base 2. Okay, so this is just a very short introduction to what merge sort is, because we'll be doing something a bit different, which is the external merge sort. Any questions on this so far? Okay. So I believe most of you all probably have covered this in your earlier modules already. So I won't dwell too much on this. What I really want to talk about is on the external merge sort. So external merge sort assumes that your data right now, because merge sort, what I said earlier, this is a sorting algorithm that is in memory. But external merge sort means that your data cannot be fitted into memory. So what you have to do is I need to put in the data in the memory part by part. So let's assume I have this initial database items. So these are my items. These are my tuples, and I want to sort it based on my first attribute, and I sort it based on the alphabetical order. So I want this to be in alphabetical order, and I have a few other notes here, which is one tuple is at most 1 block, and the memory holds at most 3 blocks. So we already said that we want to does it fit into memory? So it means that at any point of time, my memory can only have 3 block 1, block 2, block 3, and it also says that one tuple only fits into 1 block. So it means that at any point of time, I only have 1 tuple, 2 tuple, 3 tuples in my memory. Okay, so far. Okay, good. So the first thing that we want to do is we want to find out, we have a concept called runs. So we want to find out how many runs we are able to create. So you can think about it as the number of runs to be, let's say let's say how many number of tuples, how many times I need to fill up the memory. Sorry for the English. I can't think of the right words to say, but you know what I'm trying to say. I'm trying to say that so let's say for this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this 12 tuples, I know that every time my memory can only take in 3 tuples. So it means that I need to sort of fill up the memory 4 times. Okay, so because I need to fill up the memory 4 times in order to accommodate all my 12 tuples, so each time I fill it up, I call it a single run. So altogether, there are 4 runs for this example. Is this clear so far? The description of the run. So I hope this is maybe my explanation probably is a bit funny, but yeah, but the runs is like number of runs is like the number of times you really need to fill up the to fill up the memory in order to accommodate all the tuples. So this example is that the first run takes my first 3 tuples, the second run takes my next 3 tuples, and this takes my next 3 tuples, and this takes my next 3 tuples. Okay, why is it 3? It is 3 because, as we said earlier, the memory can only hold 3 blocks, and each block can only hold 1 tuple. So every time it's only just 3. Okay. All okay so far? Okay. So good. So so good that you're fine with this part. So what we do is after we create the run, you notice that we first sort the runs. So the runs are sorted. It is not specified what kind of sorting mechanism this is done in, so I would assume that essentially it is not important, but it is important that the individual runs are sorted. Okay, so after you sort the individual runs, right now this you can consider this to be the divide step, and this whole part is the conquer step. So it is exactly the same as what you see in the merge sort, just that right now, instead of everything being in memory, we now have the additional constraint. How do we fit our runs into memory? So we have the idea, or rather we know that the memory can hold at most 3 blocks. So what we do is this. So for every time we do the merge step, we always have one. So we always must reserve 1 block for my merge. So let's say my memory has M1, memory M1, sorry, a space for block 1, block 2, and block 3. So you can consider this to be block 1, block 2, and you will start to write into block 3. So this is the conceptually how this works. Okay, so you will allocate space for block 1, which is the first run, block 2, which is the second run, and the third block you'll be used to store my my merged so-called you can call it list from my earlier 2 runs. Of course, the space here is bigger than yeah, but you notice that you'll be able to accommodate the space. Okay. So what we do is it will be similar to change the color. So it's going to be the same. The pointer comes here, the pointer comes here. So it compares between A and B. So A comes here, the pointer moves over here. Now it compares between D and B, and B comes here. Now the pointer shifts. Compares between C, so C and D, E, and finally G. So now we get another sorted list. Any questions on this? Okay, so similarly, after this is carried out, we'll carry out the two runs below to have another sorted run that looks like this manner. And what's going to happen is we are going to assign block 1 now to this, block 2 now to this, and block 3 now to this. Okay, so although the space here is you can say not sufficient to block, but we'll be reading this from our secondary storage. So once we read this, once it overflows, we write this to secondary storage, and then we'll read this back, and then after that we will then continue to sort this in memory. Okay. So very quickly, very quickly, the pointer comes here, the pointer comes here. So notice that here A19 and A14 they're the same. I don't know what is the order that they want to resolve the conflict, but it seems that they will use the secondary attribute to resolve the conflict. So hence this comes here. May not be the case all the time. So sometimes they may want to just use it if it's a pure stable algorithm. So in this case, they're using the second attribute to carry out the merging process. So the first comes here. So right now A gets compared with D. This comes here, and B, okay, and so on and so forth. Okay. So finally we get the sorted output. That is this. Any questions so far? Okay. Okay. So this is what is this? This is the algorithm for it. So if let's say the memory holds 8 M blocks, we have the divide stage, and then we have the conquer or the merge state. Divide stage, we create the sorted runs. So over here, these are the runs that we create. And then in the merge state, we have the output buffer, you have the input buffer, input buffer, we have the output buffer. So, sorry. So initially, this will be, after we create the runs, this will be the input buffer, this will be the output buffer, we'll read into the buffer, and then we do the merging part into the output buffer, and we probably will write it into secondary memory as well. Oh yeah, so we will write it to disk when the buffer is full. Okay, so the number of runs decreases by a factor of n-1 in each merge pass. We will discuss and a little bit more about this when we come back after the break. So I realized that now it is the break time, but before we go for the break, I want to point out something. So I realized that I forgot to reply the Moodle forum last night. So there's a question that came out. So the quiz on which is tomorrow, the topics or the lecture slides will be the same as that in quiz 3 and quiz 4. So you can just it is like a week quiz for your quiz 3 and quiz 4. So you can just study them. Also, it is if you have not have any MC, it is actually optional for you. So if you have no MCs, you don't come. What we'll do is we'll take the best 4 quizzes out of 5. So if you feel that you don't need to take the quiz, you don't come. Yeah, so really it's optional. And will what be taught on Thursday and Fridays? No, this which is today and tomorrow, it will not be in the quiz. So I'll be going through the quizzes. No, I will not go through the quizzes. I released the answers already. So I will not go through the quizzes, but I will return the scripts. Okay, so I will not go through the quizzes unless you want me to go through. So if you want me to go through, I can go through. But if not, I think we can let it be. Or if you want, I can release the videos on the answers as well. So essentially, what is the current I would say, the current directive is that we should avoid as much physical contact with each other as possible. So which is where all these funny arrangements come about. But if you want me to go through the quizzes, right, I'm fine to do it. We can either do it on Friday or we can do it offline. So it's really up to you. You can let me know. So quiz appeals, it will be for quiz 1, quiz 3 and quiz 4, because I'll be returning you the scripts. I don't think I can provide you the scripts for 5 immediately after that. So unless we do MCQ, but I usually don't do MCQ. So yeah, I think we probably will do it. Yeah, so probably no. For the quiz 5 appeals, we'll do it together with the finals. So this is it for whatever quiz. Hopefully this is clear. You can ask me further if there are any other further questions. So okay, so the time now is 2:42. Sorry for taking up 2 minutes of your time. So we'll go for a very short 10 minutes break. We'll reconvene back at about 2:53. Thank you. Yeah, then we talked about what external merge sort is. We went through an example of how external merge sort works. And then we have we now have the general form of how external merge sort works. So in external merge sort, the memory first holds n blocks. We have the divide stage whereby we create the sorted runs, which is over here, my sorted runs. And then in my sorted runs, I have my input buffer and output buffer. I set my input buffer to be n-1 blocks. Oops, sorry, which is over here, n-1 block, and my output buffer to be over here. And then we'll then do the merge step whereby my input buffers will be merged to my output buffers. And whenever there's overflow, I will then write it to secondary storage or to disk. So the number of runs decreases by a factor of n-1 in each merge pass. Okay, let's go through some examples. Right now we have this example. Maybe you guys want to take some time to think about this, or maybe I give you maybe about 2 minutes to think this through and see how your thing may look like. So the first thing you want to do is you want to create your runs. So you write down, like, you can draw a number of runs that you have. Oh, sorry, number of runs that you have. And then you also want to create then after that you want to do this is the divide step. Sorry, then in the merge step, sorry, I was told, let me this is the divide step. And then in the merge step, how the different runs are being merged. So maybe you want to just take about 1-2 minutes, or start again at 2:57. Okay. Okay, all done. Okay, so let's see this. How do we do it? So right now we have each block has 2 tuples, and M is able to hold up 3 blocks. Right? So there'll be 2 tuples here, 2 tuples here, 2 tuples here. So how many runs will we have? So we have 4 runs of 6 tuples each. So we have 4 runs of 6 tuples each. So this is the divide step. So inside here will be tuple 1 to 6, 7 to 12, 13 to 18, 19 to 24. Sorry. So after this, we have to do the merge step or the concur step. So we will have 3 blocks. So block 1, block 2, and block 3 will be here. So these two will be merged to this. This will merge to here. So this will ultimately hold 1 to 12, 13 to 24. And then after that, the final step of the merge will be block 1, block 2, block 3, and this will hold 1 to 24. Okay, so this is how this so-called external sort would look like. Any questions? All good? Okay, let's continue. Okay, let's another example. So maybe you can take maybe 1 minute. I will start again at 3. Okay, so the time now is 3. So we have each block can hold 3 tuples, and my memory can hold 4 blocks. So it means that my memory can hold 4 blocks. Each block can hold tuple 1, tuple 2, tuple 3. And so inside my memory, I will be able to hold 4 of this. So it will be tuple 1 to tuple 12 for my run 1. Run 2 will be tuple 13 to tuple 24. Run 2. Run 3. Tuple 25 to 36. And R4 37 to 48. Okay, so this is once again the divide step. In the merge step, what will we have? How many blocks will we be using in this case? Or maybe the question is how many blocks will we be using to merge in this case? So we'll be using 3. So because right now our memory is able to hold 4 blocks. So because the memory is able to hold 4 blocks, we will now be able to put block 1, block 2, block 3, and block 4 here. Yes, any question? Okay, so maybe random. So anyway, this will be merged here into block 4. This will be the first merge step. Then the second merge step will be between this over here. Okay, so all good. So this will be how this external merge sort algorithm will be done in this scenario. Okay, now some analysis. So if let's say BR is the total number of blocks of relation R, in the first stage, it requires 2 times BR of block transfers. This is where we create the sorted run. So at this state, from here, you create so your R1, R2. So assuming there are only 3 runs, so over here you will incur the cost of BR, and over here you will also incur the cost of BR. So read and both the reading and the writing. So this will be the number of block transfers that you do. How do we know what is the number of runs to create? So fortunately, we have a formula. So the number of runs to create is the number of blocks of the relationship divided by number of blocks in memory. So this is, sorry, in the upper ceiling of it. So this is the formula to find out what is the number of runs. So basically, really, it's like how many times you need to fill out your memory in order to accommodate the entire memory, the entire tuples into your the entire tuples. Okay, and the merge pass will be this. So you can say that this is equals to your n. So n, and right now I have how to say, the height of this will be equals to, there will be a fan out factor of m minus 1. So you can consider this to be a factor of and this fan out is m minus 1. So the m minus 1 number of arrows pointing out of here. So as we know, if the m minus 1 number of arrows pointing out of here, it means that my exponential it goes down exponentially by a factor of m minus 1. And if it goes down exponentially by that, it means that my base of my log will be equals to m minus 1. And so the number of merge passes, number of times we need to go through my concur step will be equals to my log of n, which is mr by m, and my base is m minus 1 because of the fan out factor of m minus 1. Okay. Okay. And we said earlier that when we carry out the concur step, there may be times whereby our buffer will overflow, and then we have to write to memory. So write this for secondary storage. Cool. Secondary storage. So because of that, every single merge step, we also incur a cost of this 2 times the block transfers. So all in all, we have this, which is my divide, this, which is my merge. Each of them take 2 times BR. So together the cost of the transfer will be the merge plus divide which is 1, times 2 times the cost of my block transfer. Okay, all okay? Okay, if all is fine, let's take this formula and look at this example. So in this example, we have let's recreate the number to the formula PR times ceiling log m minus 1 PR by m plus 1. So do you want not do you want do you mind plugging in the formulas here and seeing what you get for this? So right now we have 48 tuples or tuples, and now each block is one block, 3 tuple. So number of block will be equals to 48 divided by 3, which will be equals to 1, 6. So BR equals to 16, M is equals to 4. The number of runs equals to 16 divided by 4 ceiling, which is BR divided by M ceiling. So 16 divided by 4, which is equals to 4. Okay, so the cost of sorry for my handwriting, it's very messy. I'm sorry. So this will be equals to 2 times BR, which is equals to 16 times log M is equals to 4. So we log of base 3, but BR by M is equals to 4. And I'm going to take the ceiling of this plus 1 times 8. Sorry, confused myself. Okay, so it'll be 2 times 16 times this expression over here. So log of 4 base 3, the ceiling plus 1. Okay, all comfortable with this? Okay, let's try this one now. So I'm going to I will be neater this time. So I'm going to be neater. Sorry, I'm going to be neater. I'm going to write the formula 2 times of m minus 1 er divided by n ceiling plus. So maybe you want to try with this question. So maybe I give you maybe 2 minutes. 2 minutes. I will start at 3:14. Okay, we're gonna start now. So thank you for your patience. So first thing to do is we want to find out what's the number of blocks of my in my relationship. So number of blocks will be equals to. So now I have 24 tuples. 24 divided by 2, which is equals to 12 blocks. So now I have 12 blocks in my tuples, and sorry, I'm a bit distracted. And m is equals to 3, and so number of runs will be equals to br divided by m, which is equals to 12 divided by 3 equals to 4. So as you say, 1, 2, 3, 4. And if we plug in these numbers into the formula, we're going to get equals to 2 times 12 multiplied by the ceiling of log 3, and this will be 4 ceiling plus 1. So here we go. So this will be the answer for this question. Okay, let's move on to the final question. So maybe just take about 3 minutes to do this. I'll start again at 3:18. Log 2. Sorry, let me see. Did I make a mistake? Let's see where. Oh yeah, I'm sorry. This is log 2. Yeah, I made a mistake. Thank you, Chun Yong. Yeah, this is log 2, not log 3. So too distracted already. Yeah, so some new developments in the COVID virus thing. So yeah, we just got some updates. So a bit distracted. Yeah, so yeah, sorry, so yeah, you will hear, yeah. Yeah. Okay for me to start. Yeah, I'll just begin by by saying that we so it says that one tuple fits only one block. One tuple fits only one block, and the memory holds at most 3 blocks. Okay. And what we want to do is we want to sort it also based on the second attribute. So this is important. It's not based on kangaroo or wallaby. It is based on the second attribute. So what we at least what we can do for, I'm going to do it in a bit of a shortcut way. Don't do it in the exam, but I'm just going to write the numbers here. because I'm lazy. So 1, 13, 3, 8, 4, 11, 6, 9, 2, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, yeah, good. So there are 12 elements here. So there are 12 elements here, 12 tuples. What's the first thing you want to do? You calculate the number of uh, of runs. Okay, so you calculate the number of runs by taking the the number of blocks VR will be equals to 12 because one tuple, one block. Okay, sorry, so because one tuple, one block, and then what you do is you find out what is the number of runs equals to number of blocks divide by m, and I take the ceiling of it. Okay, and this will be equals to 12 divided by 3 ceiling, which is equals to 4. So my number of runs is equals to 4. So one run, and we also know that one run is only 3. So what will happen is I'm going to have 17, 21, 1, 13, 3, 8, 8, 4, 11. Wait, sorry. 4, 11, 6, and 9, 2, 12. So this is my divide step. 4 runs, R1, R2, R3, R4. Okay, then the second part will be the merge step. So in the merge step, what we are going to do is, we know that it will hold at most 3 blocks. So what we'll do is, this will be, we'll consider block 1, block 2, then we'll merge it into one block, block 3, and I'm going to get, sorry. So I forgot to do this, sorry. I apologize. So I need to do this. Sorry, I'm really too distracted. So we notice that this is unsorted. So in my run, I need to sort them first. So it'll be 1, 17, and 21. So the 3, 8, and 13, 4, 6, 11, 2, 9, and 12. Okay, so in my runs, they need to be sorted. So the first thing I'll do is I'll assign this to B1, B2, and then I'll have a B3. So in the merging step, the same thing, I'm going to change the color of my pointer. So I'm going to have a pointer over here, pointer over here. So I will take we'll compare between this and this. 1 comes here, moves down. 17, 3, 3 comes here, moves down. 8 and 17, 8 comes here, moves down. 17 and 13, 13 comes here, moves down. And then 17 and 21. Okay, so this will be here. And I'm going to do the same for this. So this just going to do right 4, 2, 4, 6, 9, 11, 12. So all okay with how we got this. Very good. So the next thing that we will do is this will now be assigned to B1. This will be assigned to B2. And we will now create another new so-called merged block, which will be 1, 2, 3, 4, 6, 8, 9, 11, 12, 13, 17, 21. 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 11, 12. Okay, so this will be the final output, the merged, or rather the merged sort array. Okay with this? Okay, let's look at the cost. So I'm going to write down the formula because I can't memorize it as well. So 2 times BR times the ceiling of log m minus 1 BR over m plus 1. So BR is equals to 12. BR over m is equals to 4. M is equals to 3. So this will be equals to 2 times log of 2 log 4 base 2. And this is the ceiling of this plus 1. Okay. And I can do this in memory times 12 times 2 plus 1 because log 4 base 2 is 2. Then this will be equals to 2 times 12 times 3. So it will be equals to this is 36, 72. Okay, so this is it for this example. Hopefully, I did not screw up in the calculations. Are there any questions on this? If there are no questions on this, what I want you all to do is, can you help me with the survey? So I'm going to take a 4 minutes break for you all to carry out the survey, and I'll restart again at 3:30 with the next topic. Thank you. So we just have about 7 minutes, so we just do whatever we can. So this last topic is a continuation, in fact, of what we did in the previous lecture. So we are looking into the joins per se. So why we studied merge? So why we studied sorting, right? The main reason why is because we want to study them for joins. So we're going to use a running example. And the running example we're going to have is when a join of two relationships. So R and S, it will be like student join with ticks. And then we are going to use these numbers. The number of students is 5,000. Number of blocks of student is 100. Number of ticks is 10,000. Number of blocks of ticks is 400. So this will be the numbers that we'll work with. So so the first scenario that occurs is this. So for nested join, so this is the base scenario whereby it is like a, I mean, you can see what happens is like a double for loop. Okay, so essentially it is really like a double for loop. So you normally do this when both R and S are able to fit into memory. So this is done when both R and S fit. Then will this nested loop join, this is tuple by tuple. then will this make sense? If either one of these will not fit into, or rather if both of these will not fit into memory, we will talk about what is one other join that we can do. But this is done when both are able to fit into memory. So in the best case, you just need to transfer your blocks from relationship R, which is BR, and the blocks from relationship S, which is BS, and then you put it into memory. And then you also have two accesses of each of the start of my R and also my start of my S. Okay, so this is the best case scenario. Okay, I'm going to cover the worst case scenario, and I probably will redo this slide when I do the recording for this entire lecture. So in the worst case scenario is when the buffer holds only one block of each relation. So it means that I have a buffer, and this is from R, and this is from B. And I have other blocks of R here. I have other blocks of B over here. And because of that, what happens is that for every single time I need to go through the one block, every single tuple has got to be done. So it means that for one tuple here, I need to go through every single tuple in this block, followed by every single tuple in all of the blocks. So can you see this? So every single tuple here, I need to redo it for every single tuple in all my blocks of my relationship S. So this will be compared later on with the block nested loop, but it means that every time I do, let's say, one tuple, I go through all the blocks, and tuple 2, I also go through all the blocks. So you can tell that this is very inefficient. Okay, so in the worst case, this is what happens when one tuple has to go through all the blocks. I move on to the next tuple, and then I go through all the blocks again. So which is why you see that the number of block transfers is very large. So R is next. R is my external block. External loop, and you notice that R, the number of blocks for R is only BR, which is the number of blocks transfers it takes. So this is BR. So number of block transfers for R is only BR. But the number of block transfers for S is going to be huge. It is not just BS, it is actually N of R times BS. So you notice that it's very strange. How come N of R? It's because for every single tuple of R, I need to carry out BS number of block transfers. So for my outer loop, I only need to transfer it for BR number of times. But then for my inner loop, I need to transfer it for number of tuples of R multiplied by the number of blocks of S. So hence I have this huge term over here. Okay, this is my S, this is my R. Okay, any questions on this? Similarly, for this, this is my block SS. For my R, I need to do it one time per block. But for my block SS, I need to do it every single for every single tuple of R. Every single tuple of R, I need to carry out one block access for my relationship S. So hence, this is NR plus BR. This is for my relationship R. This is for my relationship S. Can? Okay, so the time now is 3:40. I don't want to hold you guys up. So if everything is fine, I'll see you guys tomorrow at 2 p.m. In school. Please don't be late, and please do stay safe. We have a new advisory coming out from the school. Yeah, we'll see whether is not. I'm not too sure if DigiPen is affected yet, but SRT is affected, and we'll chat more again tomorrow when we get more clarity. And yeah, all the best, and please be healthy. Okay, I'll see you guys tomorrow. Take care. Oh, please do the survey. Please do the survey as well. Okay, take care. I will off the recording now.